quantify and quantify. Shall we review this like the game? Thank you.
Hey guys, I guess you guys know where to check your grades, right? As usual. It's just on my website. If you don't know which one is yours, just let me know. I'm gonna let you know your random code, random ID, whatever ID is. I just check your grade. And since you guys are supposed to turn in your quiz 3 and make midterm on Wednesday, that Wednesday, so I'm gonna still grade it. And I think if we take a look at the schedule, per the policy of the college, the midterm grades will be due this Friday. So I'm going to grade your midterm and quiz on Wednesday, and I'll post it as your midterm and quiz grades. I'm going to just put it in there. And you'll see your midterm grades on, I don't know how you'll see it, just on Web Opus or somewhere. Just the way you have done, you used to do, right? Just check your grades. So I'm going to do a review for midterm and quiz 3 today. I'll cover more stick diagrams on Wednesday, and there's no lab tomorrow, so which means I won't be in the lab tomorrow. If you have time, you can still keep working on the lab you started last week, right? And that's due next Monday, right? It's till 10 p.m. Is that clear? All right, let's do the review. One more thing. For homework 2, I'm going to give it back to you now. The solution is posted on the website. I didn't write all the explanations, the narratives for some of the problems. I just put all the key statement over there. For the calculations, I have done all of them. I just compare your numbers with mine and see what are the issues. Okay. So let me pause. Let's start with quiz 3 first. The first problem. I've seen a lot of issues on that. So V is swept from -5 to 5. I didn't say this is a sine wave. It's not a peak-to-peak voltage. This is a DC voltage, DC sweep. That's a DC analysis, right? So the x-axis. So if you draw this, what's the x-axis? Time. DC sweep. What's the x-axis? Voltage, right? DC sweep. VV. This is TV. Different. And since this is changing from -5 to 5, and you are supposed to draw the IV curve. Is that IV curve? Yeah, V in versus V out. V in versus V out. The diodes are real diodes with 0.7 built-in voltage and no reverse breakdown. Just normal diodes. For this one, no matter which direction it's being blocked, right? No current is going to flow through the circuit. So whatever V is, there won't be any current because there's no load. So whatever voltage is here is going to be directly translated or directly transferred to here, to V out. I know there's a 0.7 built-in voltage, but however, because there's no current flows through this circuit, so it's not being applied to here at all because there's nothing. This branch of the circuit will never be conductive. So just like this. And that's V in from -5 to 5, and that's V out from -5 to 5. Oh, 5. What about second one? Is it the same situation? Yeah, it's just blocking the circuit. So nothing can flow through here. Still the same result. None of you made it right. None. 0. So I give it back to you. This. So remember the p-n junction. Let's try to understand this properly. Since everybody knows there will be a depletion region here in the middle of the p-n junction, and the holes diffused to the right side and the electrons diffused to the left side, and to form this depletion region. Why? Because the electrons flows to the left and fill into the holes, so it becomes negatively charged, and the other direction as well. So the holes comes over, combine with the electrons. So normally it's neutral, and after that, after all these combinations, and apparently there are more holes will appear on the right hand side. So it's appear a positively charged on this side. So it's able to form a electric field. So whenever you are trying to forward bias this diode, it has to overcome this electric field. So what's happening in real life is, it's at the very beginning, if there's no voltage applied to the diode, this guy has a certain width, right, for the depletion region. But after you forward bias it, it's going to compress this depletion region, make it thinner and thinner. It's almost 0 whenever it becomes conductive. So whatever the voltage is doing is to compress this depletion region, make it thinner and very thin, which is close to 0. So it's conductive, becomes conductive. So the electrons can directly tunnel through this depletion, very thin depletion region, and reach to here, because this is relatively strong electric field. So the electrons will swim across that depletion region, or you can say the holes will just cross that region, right, and reach the cathode. That's why it becomes conductive. So this voltage is just to compress this depletion region, make it thinner. Okay, that's how that works. So since it has to be larger than whatever here, in silicon it's normally 0.7 volts, 0.6, 0.7. And if we assume this is 0.7, doesn't matter, you just need to draw the circuit for me. It can be 0.6. For gallium arsenide, I think it's somewhere around 0.3. But anyway, you just don't have, you cannot just draw 5 and 5, minus 5 for the voltages, right? It has to be 0 point something. And whenever it's positive, it's going to apply the forward bias this diode. Whenever it's larger than 0.7, it will be conductive and stabilized at 0.7. Whenever this guy is negative, the same thing. So it's going to be conductive in that direction, and this diode will clip the voltage drop across these terminals to minus 0.7. Right? For this one, the Q point, determine the Q point values and draw the DC load line of the following circuit. I've seen a couple problems, not just here, but also in your homework. Whenever the BJT is already connected like this, it's already self-biased, which means the VCC has biased this BJT at a certain Q point. So the Q point is not just 50% of the IC max, right? Whenever you are being asked to design the circuit, you are trying to find the Q point in the middle. However, this has been biased already, and it's not asking you to design the circuit, which means You don't want it just to find the Mx and divide it by 2, right? Of course, that's a better Q point, right, to use. However, it's not asking you to design it. So directly use the Q point values already being used for the circuit. So all these points are Q points. But not all of them are the best. There's probably the only one you want to use, which is 50% of Mx right here. So this one, you don't know because it's already biased in a certain way. And you assume VBE to be 0.7 volts. You can find the ICQ and IBQ, VCEQ, all these values. Where do you want to get started? Base current, yep. So IB, which is also IBQ because this is already biased, self-biased, it's ready. IB equals to IBQ, which is VCC minus 0.7 over RB, which is 10 minus 0.7 over 400K. Yeah, let's calculate it. What is this? 9.3 over 400. This much milliamps, so it's 23.25 microamps. And what is IC or ICQ, which is beta times IBQ, which is 100 times that will be 2.325 milliamp. So what is VCE? VCC minus ICQ times RC, which is 10 volts minus 2K times 2.325 milliamps. So this is roughly 4.65. No, exactly 4.65. So 10 minus that one will be 5.35 volts. To construct the load line, just draw this, boom, and that's 5.35 volts, and this is 2.325 milliamps. So there must be a max value here and here as well. We can calculate that one. So IC max equals to VCC over RC, which is 5 milliamps. It's pretty close to 50% of the Imax. And VCE, the maximum VCE when there's no current, so all the 10 volts will be dropped across this C and E terminals, and you're getting 10 volts here. Okay, if I have more space, we can draw this a little bit nicer. Is that clear for this one? Easy, right? This one. So the differences are you have a negative voltage being shorted to the E terminal, and the base is grounded, and you have a extra resistor being shorted to the E terminal. And it's asking you to design the circuit, which means you want to specify the values for RC and RE. They're not given. A problem. So before we move forward, you can actually find out RC in a second. How? See here, the goal is whenever I see you got a 2 milliamps current flows through the BJT, VC, which is the voltage at this point, is 5 volts. Whenever there's a current, which is 2 milliamps. Oops, you know the voltage here, you know the voltage here, and the voltage drop, you know the current. Can I get the RC? Of course. So RC is 15 volts minus 5 over 2 milliamps, which is 5K. Done for RC, 10 points. What about RE? Remember this equation, IC equals to IS times E VB over VT. So just plugging all these numbers in there. 1 milliamp equals to IS times E 0.7 over VT. And when IC is 2 milliamps, there will be a different VBE. Although it's very close to 0.7, but we don't know what is that one yet. And VT is a constant. Its room temperature is going to be 25 millivolts all the time. And you do a division on the two sides of the equation, and you are getting this. And natural log on both sides. What is natural log of 0.5? Is that 0.7? Negative 0.7. Move it to the left. Wait, that's tiny. So this one minus this one, which is 0.7 plus 1, 2, 3, 0.0. It's very close to 0.7. That's VBE. Is there anything wrong with the calculation? No, that's right. You know why? Because from 1 milliamps to 2 milliamps, this is a super minor change for the IC, so that's why it's not changing a lot for the VBE as well. That's why you can see that if you change your IC from 1 milliamp to 2 milliamps, then the VBE only changes from 0.7 to 0.7175 volts, right? Tiny. So which means for this curve, it's really exponential. Here's 0.7, here's 0.7175. So you got a huge current gain. Anyway, that's VBE, which means that's B, that's E plus minus, which is this voltage. So what is RE? We're trying to find out RE. And now we know VBE is 0.7175 volts. And we know this guy is minus 15 volts. And we want to know VRE, because if we know the voltage drop, and since we already know IC or IB, we can directly calculate IE. So IE is already calculated, it's already known. And if we know the voltage drop, we can find out RE. So what's the voltage drop across this resistor? Plus minus is 0.7175 volts. And flip it, so the voltage from here to here, which is also voltage VE, the terminal E compared to the ground, will be negative 0.7175 volts. And you know this voltage is minus 15, so you can use VE minus 15. You can get VRE, and then use VRE over IE, so you can get RE. Okay, that's the goal, to find out RE. So IE, since we know the IB already, do we know IB? We know IC. IE is 1 plus beta IB, and IB is IC over IB over beta. So IE is since IC is 2 milliamps, so that will be 2 milliamp over 100. You got IB, and times 1 plus beta, which is 101. You get IE. It's pretty close to 100. Sorry. (101) times 2 over 100. That's it. Okay, plug it in to this equation. RE will be VE, which is negative 0.175 minus 15 over 2.02 milliamps. Right, that'll be 15 minus this, right? Plus 15 minus 0.7175 divided by 2.02. So it's 7.07 kilo ohms. Done. I hope this is right. There's a chance like I have any mistakes in the calculation, but you will verify by yourself. can we turn anything in on Wednesday? If I made a mistake over here, you made the same mistake. It's embarrassing. Any questions for anything on the quiz 3? No? If you like, yeah, I think so, yeah. It's hard to, I don't know if we can get a model, correct the model for this BGT. So currently, I'm trying to teach my kid to identify all the states on the map of the U.S. And have you ever seen a TV show from Jimmy Kimmel? And he did an interview on the L.A. on the street, and to ask someone, just randomly pick up someone to find out which states are these on the map, or they showed a map of the world. Ask that person, just find out one country on the map. And she couldn't even find out one. Not just one person, a couple of people just couldn't find out any one country on the world map. I'm just wondering, is that common or is rare? Kind of. But even for the states, they couldn't even find out all the states. What about, so did you learn it in primary school, in middle school, high school? Is that in the exam? No. If I have a map of the country, can you find out? I mean, is there any states you cannot identify? There are some. I mean, if I just randomly point to one of the states on the east coast, the small ones, I mean, is there any of the states you cannot identify? Just in general, might be. Yeah. Yeah. But if I give the map of the world, you will. I'm pretty sure you are able to identify at least 10 or 20 countries, right? Yeah. All right. Sometimes I understand it's for myself. For some of the states on the southeast, some of the states look super similar, and maybe can mess up with the older, like Alabama and Louisiana, Georgia. These are pretty close, right? But I know it's Georgia, Alabama. What's next on the left? Arkansas, no. Anyway. All right. What about this one? So combine these two resistors, and you are getting a 1K resistor. And that 1K resistor is in series with this 1K resistor, and they will form another 2K resistor. So it looks like this. Yeah, another question. Which one on this R2R DAC? Where is MSB? Where is LSB? And why? Yes. Because this voltage is not being divided by that many resistors. So you are getting a higher voltage here from this guy. That's why this is MSB, because this 5 volts contributes a lot more compared to this 5 volts contribute to the VL. So after we simplify the circuit, so this 2K in parallel, 2K resistors becomes, and this 1K becomes 2K here. That's 2K, 5 volts, 2K. Have you realized that superposition is super important recently, but not in circuit 1? Not just over here, but also in the op-amp. Remember the when we are trying to add an offside, DC offside from the other terminal, it's also a superposition. You just ignore the other one, you just add a DC voltage across the resistor. It's going to lift the signal up. No matter what the AC signal is being applied to the input, it's going to lift it to that DC level. Right? It's also superposition. How to understand it? I mean, you just directly add a DC voltage across the resistor. Or trying to use a mesh or anything else is complicated. But if you just think about the entire thing using superposition, it becomes super simple. It's just adding a DC voltage to it. Yeah. All right. And when you are looking at it, just treat whatever here as the load. That's a load. So that's the voltage divider. You know, since you guys have learned Thevenin's equivalent for so long, and you can find out it's actually super important and useful. And if you have this kind of circuit, and people are asking you what's the Thevenin's equivalent, what is it? Yeah, 2.5 for the ETH. Why? Because this is a voltage divider, so whatever voltage here will be the ETH. Right? So you're wondering why the voltage here? Because I'm treating this one as a load. So whatever from this point to the ground will be RL. I don't care about what's inside, it's just black box. It's a load. I'm going to remove it when I'm doing ETH and RTH. So whatever the voltage here will be ETH, and apparently that's a voltage divider. That's dividing this by 2 halves. So I'm getting 2.5 volts over here, which will be the ETH. And if I short this guy, I'm looking inside. It's just 2 resistors in parallel. That's 1K. So the equivalent circuit of this one will be definitely 2.5 and 1K. Right? Done. And then just come back and replace whatever here using this one. Replace this guy. Use this one. It's 2.5. That's 1K. And there's another 1K just after it. And here's VO. 5 volts again. That's 2K. That's ground. And these are 2K resistors. And I'm not done with this voltage source yet, because I'm not finding out the. So this voltage is not the final contribution from this source to VL. I have one step to the VL. So whenever you are doing superposition, you just assume this one is being shorted, right? This is shorted. So you got 2K, 2K. What is VL? 2K here, 2K here. Yeah, 1.25. So the contribution from this guy is 1.25. And when you are looking at this voltage source, it just short this guy, and that's a 1K. You got 2K, and 5K is being divided by 2 halves, 2K, 2K. So VL contribution to the VL from this guy will be 2.5. So the final result for VL is, because this is asking you to solve for VL, so just find out this 5 is contributing 2.5 to it, and this 5 is contributing 1.25 to it. So just add them together, superimpose them together. You're getting 3.75 volts. For this one, since it's asking to draw the states for the for the SAR ADC, you don't have to draw the condition which is not being used, right? Just make it easier. And start from 1, 0, 0, 0. That's a, you see, if you look at the problem, it's asking you to show the digital voltage and analog voltage, the two voltages and the state. If this is a 4-bit SAR ADC, how many states do you have eventually? N plus 1, which is 5. You just need 5 states. And that's 1, 0, 0, 0, which is digital, and the analog voltage will be 5 volts. And what's next? 5 compared to 6.2 is smaller. Keep in mind, the 6.2 is being fed into the non-inverting, and the 5 is to the inverting. So when 5 compared to 6.2 is smaller, right? So we want to shift everything to the right and plug in the 1 in the front. And this one is 5, the next one will be 2.5, so this becomes 7.5 volts. So we got 7.5 volts over here, which is larger than 6.2, so it's going to be a 0, digital 0 of the comparator output. And it's getting a 0, and you want to shift whatever here to the right and plug in the 0 in here. That'll be 1, 0, 1, 0. That's 5, 2.5, 1.25. So 5 plus 1.25 is 6.25. Still larger than this. One, 0, 0, 1. 5, 2.5, 1.25, 0.625. So this becomes 5.625. Smaller. And you still have this one is still here. You want to shift it to the right. So next, shift this out to the right and replace it with 1. Still the same value, but it's not the original one, since this has been shifted. And it's plugging another 1 here. And it's still the same voltage. And that's the final result. All right. And keep in mind, the final converted analog voltage is always smaller than the input voltage, or sometimes equal to that, equal or smaller than that. So if you see a value which is the calculated value is larger than that, which means something is going wrong here in the loop. You just want to go back and fix it. That's how you can do a quick check with all the results. Next one. Draw the V in VR curves of the following circuits. When V in is swept from -5 to 5, it's reeled out 0.7 volts built-in voltage and no reverse breakdown. So -5 to 5, that's a DC sweep. So X and Y axis are both voltages. So you don't have any time domain analysis. So -5 to 5. For this guy, this circuit is not doing anything, it's just blocking everything. And this one is blocking all the positive voltages, and this is blocking all the negative voltages. Right? So this will be this, I guess, 0.7, negative 0.7. What about here? So this circuit is not doing anything, it's blocking the circuit. It's an open circuit. And this one, whenever the positive voltage being applied to the VL is larger than 0.7, it becomes conductive, and the voltage, any voltage higher than that will be clipped. So we'll stabilize that 0.7 volts. So definitely you know this part is going to be this. Why? Because any positive voltages will not go through this part. This guy is blocking everything, right? So it's not going to affect this one. That TV is not working. Well, But whenever this voltage is negative, so the voltage here is higher than here. It has to be larger than what to make it conductive, to run the current through this channel. So of course it has to be higher than 0.7 at least. Right? And you want to make this, you want to make here positive. You want to push the current in that direction. But this voltage source is trying to push the current in that direction, in the opposite direction. So you have to invert it first. You are not going to actually invert it, but you are just trying to overcome that voltage difference. Right? So this is not helping. This guy is not helping. Why? Because you want this, the cathode of the diode to be lower and here to be higher. How much higher? 0.7 volts higher in order to push something through it. But this voltage source is lifting the voltage level at the cathode up. This is how you understand it. It's lifting it up. So it makes it even harder to overcome that, to make it forward biased for the diode. How to make it forward biased? It has to be larger than 2.7 volts in order to forward bias this diode. So whenever the voltage is at where, then it won't going down anymore, because current is going to flow in that channel and it's going to be stabilized at that voltage level. Where? When you are trying to give a negative voltage over here, which means this is higher, this is lower. You have to give a 2.7 volts drop at least, because this guy is lifting the cathode by 2 volts. So you need a 2.7 volts to make it 0.7 volts higher. So what's the voltage here? So 1 is going to be clipped. Yep. Next, find VB and VCE. IB is 10 microamps, so IC is 1 milliamp. So VCE equals to VCC minus VRC, which is 5 volts minus 1 milliamp times 3K, which is 2 volts. So VCE is done. What about VBE? IC equals to IS, E VBE over VT. So VBE is VT times natural log IC over IS. It's calculated. VT is 25 millivolts. IC is already calculated. IS is given. So you can calculate for VBE very quick. Number 2, replace the 10 microamp current source with a resistor and 5 volt voltage source. So what resistance is required to result in the same operation? In short, I just want to replace this current source with a voltage source and a resistor to make a 10 microamp current flow to IB, because you cannot, if you want to keep the same operation, you don't want to change all the Q points, which means IB, IC, VC, all these points, right? Those are DC points. You're not trying to change it. So whatever 10 microamps is being supplied by the current source, you want to do the same thing here. If you replace this guy with voltage source and resistor. So we just need to know what the resistance is over here, because this is already given. It's 5 volts. It has to be 5 volts. So only voltage source available. And how can I make a 10 microamp IB? It's trivial, right? Because here's 0.7 volts. There's no resistor connected to the emitter, so 0.7 volts here. So RB has to be 5 volts minus 0.7 over 10 microamps, which is 4.3, 0.43 mega, 430 K ohms. Next.
Would you use the 0.7 or would you use that calculated?
Oh yeah, calculated. Yeah, that's a good question. VB, yeah, whatever VB you calculated. Mm-hmm. Is the following NPN BGT operated in linear saturation or cutoff region? Determine the Q point and draw the load line. So I'll just assume, because all the equations, all the beta, alpha, all the equations are based on the, so this guy is being operated in a linear region. If it's not in the linear region, you cannot calculate anything. So I have to assume it is operated in the linear region. So IB is 12 volts minus 0.7 over 150K. So this is 11.3 over 150. That's this much milli. So 75.3 micro amps. IC is beta times IB, which is 100. Didn't say. 100. .53 milliamps. And so VCE equals to VCC minus VRC, which is the voltage here, 12 volts, minus the voltage drop across this resistor, which is 7.53 volts. So apparently this is larger than this, and you're getting 4.47 volts to be dropped over VCE. So the requirement to make the BGT operated in a linear region is to have VCE larger than VBE. Your VBE is only like 0.7 something volts. So 4.7 volts is definitely larger than VBE. So it's in linear, larger than VBE. Determine the Q point. It's calculated, so that's already biased. It's already biased at VCEQ. So all these points, all these values are the Q points, right? So they are already calculated. Just directly use these numbers. And draw the load line. You're going to find out IC max. So what is IC max? Whenever VCE does not have any voltage drop, and you are getting 12 milliamps, and whenever there's no current, all the 12 volts will be dropped across VCE. So you're getting 12 volts. But based on the calculation, IC is 7.53 milliamps. It's larger than 50%, so it's somewhere here. So that's Q point, 7.53 milliamps. And x-axis is which is a VCE cutoff, which is 4. Oh no, that's a VCEQ, which is 4.47 volts. Okay. Next, just narratives. Yeah, as long as you can explain all the effects, it doesn't have to be official, just showing you can understand it. So do not try to memorize anything. Just draw the picture and explain what's happening there. I'm gonna give you the points. Because I hate memorizing all these paragraphs when I was in college. So I will never let you guys to do that. Not like just picking up one word. That's not a word I have seen on the textbooks. I'm gonna take 1.0 from you guys. No, I'm not. That's awful. All right, that's everything for today.